Okay, welcome to lecture 14 of Geology 2017. So we continue the discussion about sedimentary environments, mostly depositional environments. In the previous lecture, we worked mostly on continental environments, so we discussed quite a bit about alluvial fans as well as some of the braided and meandering styles of river system. So this was to give you some perspective of the environments where we find specific sedimentary structures. So we saw the importance, for example, of trough cross bedding in some of the point bars that we find in meandering systems, or the mid bars that tend to form those gravelly accumulations and sandy accumulation that are more typical of braided systems. Today we change subject, we rather move into the environment that is more transitional between freshwater systems and saline water systems, so the sea. And so we look at all the different depositional environments that are found pretty much on the coast or the coastal regions of a continent. So you have in the background the white Dover cliffs, which are certainly a good example of a highly erosional coastline. So we learned that when the coastline is really erosive, you tend to have relatively steep slopes that develop, and so you see in the background there some very beautiful cliffs, and which are whitish in color because of the calcareous formations that compose those rocks. And it's interesting to see how the sediment accumulates in alluvial deposits just off the cliff, which often is reworked by the ocean currents and waves. So today we are really going to focus on understanding the processes that contribute to the erosion of coastlines. So we learn, for example, that the erosional processes that work on cliffs like this are mostly a combination of the saline concentration that is present in the water, as well as the hydrolysis that contribute to the action that weathers these formations. So if we move into a description and start to learn some of the technical terminology that pertains a coastline, we have to sort of look at classifications that look mostly at the depth with respect to the seawater level. So many times we distinguish a continental crust that is represented by a couple of environments, which are the continental shelf and the continental slope. And in the continental shelf, the maximum really depth that we reach commonly is on the order of 200 meters below sea level. And these represent the limit that is subdividing essentially this portion with the continental slope, which increase, as the name suggests, the slope, which will usually move on more than 7 degrees and is many times much deeper. So we go down roughly to 2000 meters depth or more in some cases. These depths can reach 5000 meters in abyssal plains. So in these environments, because of this, we generate different sediments. So many times on the shelf, a lot of the coastal regions have influence on the sedimentation processes that leads to the deposition of materials. So detrital terrigenous sediment is mostly abundant in these regions, and so things that are shedded from alluvial fans, for example, on erosions, so major mountain ranges, will tend to firstly accumulate in this region. So we have quite a bit of clastic sedimentation forming. On the continental slope, we will have those mechanisms that tend to transfer this sediment in the abyssal plain, and then abyssal plain will be characterized by a variety of sediments, but we tend to have those more wacky or wake-rich sediments, or mud-rich sediments that are formed through autogenic and biogenic processes. So a lot more influence from organisms that live in the seawater and then die and precipitate and become the cement that essentially glues some of the terrigenous particles and also this additional autogenic particle. In the assignment I gave, for example, there is a question about glauconites. So glauconites are sediments that tend to form through autogenic processes that they are essentially precipitated allochemically of ocean water that is particularly enriched in potassium, and so you get these phyllosilicates accumulating on shelf-filled regions. So they are a good indication usually of relatively low sedimentation rates, because when you accumulate those allochemical sediments, it's an indication that you don't have really a lot of supply of terrigenous materials. So because of that, it's important also to know glauconites, because they represent a good marker when you're trying to understand sedimentation processes, and they are also important for paleogeographic reconstructions, because they give you an understanding of the potential location of shelf settings. The shelf, remember, is the margin of the continent that have been submerged by what are called transgressive events, in which the ocean is rising periodically, but this can occur over secular times, really, so very long time. So in a state of flooding, you will form these shelf settings which are particularly enriched in biota, and so that is also another imprint you will find in the sedimentary processes. So we have a lot of oscillation. So if we look at processes that control desedimentation that occur on continental margins and abyssal plains, we can certainly differentiate a few of them. So certainly tidal variations are one of the most critical, and in fact in this diagram you have an illustration of the displacement of the oceans that occur in response to changes in gravitational forces that are related to other masses that are away from our planet, which are dominantly the moon and the sun. So for example, when we reach the equinox, which is a point of alignment with the equator of these planets, we tend to have the formation of a major bulge, and this bulge is essentially increasing volume across equatorial regions, and it will depend again on also on the orientation of the planet, so the precession axis. So these bulges are dynamic and they are essentially varying in geographic location depending on Earth rotation. So we tend to have what are called diurnal tides. So we tend to have a movement that is cyclic. The water will either rise or subdue in response to tidal variations, and this is often associated with currents as well. So we have major currents that either move towards the continent and they are commonly called flooding events, or we have phases that are the ebb currents that will tend to depress essentially the level of seawater, and so we have that the waters migrates outward, and this is often really important for the sedimentation processes. So now that we have sort of the perception of this process, it's important to mention that there are two bulges. So we have one that is contraposed to the other, and they are actually illustrated here. So you have thickening in this related to gravitational force again, and then you can think of this as we are shifting the planet, so we get also the equivalent bulge, although usually the elevation is slightly lower on the back of the planet Earth, so the back side with respect to the Sun and Moon. So when these two planets are aligned, the bulge will be maximum. But again, if we have two and you consider a 24-hour rotation, that makes up for essentially two phases of rise and two phases of depression, which will correspond to a variation every 6 hours. We have also monthly variations, which will be essentially linked with the orbit of the moon. Usually when we get full moon, we have the maximum tide, so it's important to sort of refer also to these other periodicity. So periodicity is really a function of the orbits of the planet around the sun, because there are also periods in which we are closer to the sun, and so the oscillation will vary also as a function of these factors as well. So I was mentioning these 6 hours, so if you have a twice daily tidal cycle, you have to expect a phase in which we'll have high tide and then progressively move into a low tide, and this will occur roughly in 6 hours. So if this progresses many times, if this process progresses over time, gradually we tend to have a progressive increase in the velocity of the flow, which is maximum usually at the inflection point between a high tide and a low tide, which instead are identified because they are phases in which we have slack water. So if you remember when we mentioned that we have those typical flazzer bedding structures, they have a good fitting with this type of process, because it's when we get those slack phases that we tend to form deposits of mud over sandstone. So what are called mud drapes on ripple marks will often get preserved because of the polarity of the clays, and when they stick together they tend to get trapped essentially in these flazzer or lenticular bedding sediments. So that's one really important structure that will be associated with tide dominated and depositional environments. So another aspect is this that is illustrated here. So we tend to have the flow of offshore as tide falls, so flow will move out of the coast, and again this is called an ebb tide current, and instead you have your flowed tide current when the flow is onshore and the tide is rising. And so this effect is responsible over a very long period of time, so several years, for example those herringbone style cross stratifications that we also discussed during lab time. So these marine and coastal environments can be recognized if we have a good understanding of these sedimentary structures. If we look more in detail at some of the terminology with respect to depth-related subdivisions of this marine depositional setting, we can certainly differentiate the neritic zone as the one that is essentially between the coast and the shelf edge break, which is that one of roughly 200 meters. The continental slope becomes the bathyal zone, which again will range between 2000 and roughly 4000 meters, although it can vary depending on the type of continental margin. And often we have the abyssal zone, which can go down to 5000 meters. But for example, if you have an oceanic rift, this could be actually a little bit higher because, as you know, we have plumes, hot plumes that are pushing up the crust, and so we have a slight inflation. So many times we have a rise of the oceanic crust, which will lead it to abyssal zones that are on the order of 2000 meters. In some other instances, we go into more subduction related zones where the opposite is true. So you will end up forming trenches. So in the Adal zone, which is below the 5000 meters, you can get these depressions that will reach in some cases more than 15 kilometers of seawater depth. If we focus on the neritic environment, many times a classification is used based on the energy of the environment because it does have implications for the sorting of the sediment as well as the grain size. So for example, in the foreshore environment, which is the one where we have the usually over a meter variations related to wave action of seawater, we tend to have quite a bit of reworking taking place on coastlines associated with the wave action. And so you tend to have fairly coarse materials, so sandy and gravelly materials will accumulate in some of these coastlines. If we move down, usually below the action of the superficial waves, we enter the area of the shore face, which again is commonly an area where the action of the waves is still present, although with a low intensity, because in this case this is a zone that is submerged all the time. The foreshore instead will get periodic exposure, so you can walk basically on the foreshore, which is essentially a beach, for example. So in the shore face, then you have still the action of superficial waves, but it's more limited until you reach the limit, which is the fair weather wave base, in which we move into the offshore transition zone, where we don't have really a lot of action of superficial waves. So most of the cases of hummocky stratification, hummocks will be found in this region, and they are mostly related to storms. So if we have a major storm, also these sediments that are found in the offshore transition can get perturbed, and they will get significant structures forming in them, which could be, for example, the hummocky stratification given the high energy of a storm or a tsunami or other types of major disruptions of bedding. Below this storm wave base, so where you don't even have actions of waves that is caused by storms, so you enter the offshore domains. And so here, of course, we have much more quiescent depositional settings, and so we accumulate the majority of the finer fraction sediments, which are commonly traveling off the coast in suspended loads. So these regions are still part of the shelf, don't forget that. So an offshore is still before the shelf edge break, so we are on a depth of roughly 200 meters. Many times the sedimentation is perturbed by these characteristic features that form on the coastline when we have a freshwater system such as a river system interacting with the sea. So in this case we have essentially a synergy between continental factors, so interland related factor, and the ocean that has also implication in controlling the deposition of sediment. Many times this environment is termed a delta because of the characteristic geometry. You can recognize, if you look carefully, the triangle that is typical of the Greek letter. So this is a sedimentary environment that is particularly important because it represents one of the areas where we have the highest load of sediment depositing at the contact again or the mouth of a delta. So when essentially the river system meets seawater. So the morphology of delta will be highly variable as a function of a number of factors. We can consider, for example, the type of river system. So you can have meandering or braided river system, which usually carry different type of loads, and so both suspended and bed loads will be different, with the suspended load much more abundant in meandering systems. In some exceptional circumstances, we also have conditions in which alluvial fans are very close to sea, and so they can protrude into the seawater and form marine fans that will be very coarse, because as we saw, the poorly sorted material that is part of alluvial fans is again an indication of little transport. So usually the longer the river system, the finer will be the fractions that are deposited. One good example is the Mississippi River that goes across the United States and enter the Gulf of Mexico. So in those circumstances you have very muddy materials that are actually deposited. Okay, so remember the delta is really critical, and we have different types of processes. So I mentioned different river systems, and you can get also the action of the waves will remodel many times a delta. So in this case you have an example that is more sort of resembling the delta here with a major deposition. The action of the waves has remodeled this coastline and redistributed in spits of likely mud and sand over the side. So wind and the action of the waves can actually redistribute and consolidate these sediments that accumulate at this interface between seawater and freshwater systems. So this results in different geometries of deltas. You have the more classic here with essentially the two cities that were sort of founded in Egypt that really stands on these two terminations of the Nile River system. So many times if you have multiple branches of rivers forming, you tend to increase the size of a delta significantly, and in this case we have also evidence of the action of the sea that has redistributed part of the sediment along the coastline. But this is a very classic, sort of historically, is one of the first really deltas that should come to mind, and also because of the importance of the Nile in Egypt. Also, Rosetta is quite famous as a city because of the discovery of the Rosetta Stone, if you remember from history. So archaeologically speaking, it's very renowned because the French basically identified this important stone that essentially unraveled the possible translation of the hieroglyphics, which is the writing that was in use more than 2000 years ago by Egyptians. And so they found this stone that is now preserved in the British Museum in London, and has basically inscriptions or incisions that represent the same type of script and stories that are written both in Greek and in this hieroglyphic, and also some other languages, which I think is local Egyptian. So interesting to also know about this fact, because it basically opened up our understanding of the Egyptian civilization. Other deltas that are quite important are the Mississippi Delta, and you see it completely different morphology. This is a river-dominated delta, so we can see the effect really of a major supply of sediment. So if you have a very large river system that is sort of representing a prominent sediment load, many times it will tend to form levees and accumulations that protrude towards the sea. And so you have extensions and digitations that form like fingers, which usually are highly vegetated and become essentially land that extends as a promontory, basically. In other circumstances, like the Rhone Delta in Europe, we find rather obvious the effect of wave action, which tend to form sandbars and islands that then characterize the coastline. So these are still what are called prograding delta. So you have to imagine delta as always a prograding body, so it will always build up sediment and increase essentially the area of land that is protruding towards the sea. But the morphology can change significantly. So in this case, for example, you get this major extension of sandy material on the sides of the delta mouth, which are an indication really of the action of the waves which are dispersing the sediment. So rather than concentrating sediment in a specific location, you have that the progression of the delta is much slower. It's still progressing, but as a result you get a much larger area that is influenced by the depositional system of the delta. And then you have this other instance, which is a constant reworking, which is found either in Bangladesh or India. So the Ganges delta is quite prominent, it's very extensive, and it's often linked to a very complicated network of streams that consider, for example, the Ganges River, but also the Brahmaputra and other river systems. So in this particular context, the delta is dominated by tidal currents, and so the oscillations in currents tend to cause quite a bit of reworking in the sediment load that is deposited through this intricated system of rivers that bring essentially massive amount of sediment to sea. And so you can see these bars much more elongated, so you get these islands that are essentially displaced and reordered in preferential directions that are concordant with the major tidal flows. One thing I've forgot to mention about tides is usually that we have a range of tides, and these will often be a function of the coastline and the depth of the sea. When you have shallow coastlines or shallow seas, the energy of the waves is much more pronounced. Instead, when you have deep, so if the water is deepening very fast, we tend to have these situations where the tides will be more pronounced, and you get a lot of reorganization of the sediment due to macro tides basically. So we can distinguish very small oscillations that are linked to tides, which will be on the order of a few centimeters, but in some cases, if you have macro tides or mesotides, this variation can exceed several tens of meters, and in those cases you get these situations that are much more controlled by the variation in flow, which would be, for example, the eastern coast of Canada. So in Newfoundland, all those regions are really affected quite significantly by tides. There are a number of sub-environments that we can recognize in delta. So if we take the example of the Mississippi in a highly prograding delta in which you form these digitations, many times you have what is called the delta top forming, which is essentially found at the mouth of the delta. So many times you have relatively planar stratification that will form in this top part of the delta. This usually leads to a depositional system that is very coarse, and it's sort of let's say, very influenced by the river channel bedload. So lots of bedload material is deposited in this location for obvious reasons. So many times you essentially increase infinitely the section of the river system when you reach sea. So you have usually that the flow velocity will drop dramatically, and so the coarser fractions, similar to alluvial fans, get deposited straight away in a submarine environment. So you tend to form sandy mouth bars, for example. Many times you form also overbank areas, so areas that are in the immediate periphery of the river system can get flooded periodically and will tend to be again represented but relatively fine fractions, because this is mostly suspended load material that gets deposited in these regions, which are part of the delta plane. And so these are commonly called crevasse splays. Another important aspect of deltas is the progressive decrease in grain size of the material that is deposited. So in the delta front, we tend to have what are called pro-delta deposits forming. And so many times these will be much finer grain, so they will tend to be more sandy or silty materials, and in the delta front we can then accumulate even finer fraction more distally from these centers of deposition, which will be dominated by suspended loads. Often these parts of the levees will be highly vegetated, and they accumulate quite a bit of peat, and so many times delta are important depositional environments to identify in paleochannels, because they contain a lot of organic matter, which is important for from the perspective of fossil fuels, identification of fossil fuels, as well as uranium resources. So in essence, one of the characteristics of these systems is an inversion in the stratification of the deltas. We'll see some example of this concept and clarify that, so you don't have normal grading in these systems. So that's a good example of a conglomerate that is accumulated in essentially a delta plane. So many times you get these situations in which conglomerate deposition can form because you had, for example, a channel that was present in the plane, and then you have situation which this situation can change. So you have combinations of levees, related sediments, as well as relatively permeable sediments and coarser fractions, which again are linked to the channel flows. So important to highlight in this case what I was mentioning, so the accumulation of organic matter. So you can see some pit here or lignites accumulating at the bottom of this more gravelly layer. This is an indication that again the channels are dynamic in the system, so they can change their position very rapidly. This is a cross section of a delta lobe. It's trying to explain how the prograding occurs. So we are revisiting some of the concepts I've mentioned. So usually delta slope is relatively shallow, but still it's over the threshold, widely over, I think, the threshold we saw for braided river systems. So you have to imagine quite a bit of gravelly material can form and get transported through the delta slope. And so we have these mouth bars that form, and then you have more deposition of silty materials and form those pro-delta muds, and then you have marine shelfal deposits that sort of join and are less influenced by the prograding delta. So over time we tend to have what is called a combination of prograding sediments. So they are coarsening upward successions. So that's the important distinction we can make. For example, if we compare a delta with an alluvial fan, where we saw in the previous lecture that the majority of the deposits are quite abrupt and tend to form coarse gravelly material at the bottom, and then you have a fining upward sequence, especially in those hyperflow, hypervelocity conditions. In this case, we form multiple deposits with classic cross stratification, and so this often leads to essentially an overlaying sequence that will have initially fine material, and then at the top you find the coarser material basically, and that's because the delta is progressively growing towards the sea. So the prograding aspect is influencing essentially the vertical stratification of the sediments and shows at the top usually coarser material. So you have an example of delta mouth here with bar deposits which are coarsening-up. So you find essentially siltstones here at the bottom which show quite distinct stratification with preservation of organic matter. So muds are deposited, and at the top you find more sandy material. So sandstones are preserved. In this case, they are quite oxidized sediments, and so that's clearly an indication that you have a prograding situation. So you move from muddy materials that are more typical of the slope of the delta. So the delta in this case would be the pro-delta deposits which are found in the delta front, and in this case these are the type of sediments that represent that region. Then you move into this region, which is the sandy mud bars. But of course these are sort of occurring in different locations, but we find essentially that in a vertical section these two accumulations are together, which is a good indication that the prograding aspect of the delta led to a change in the deposition of sediments, getting a coarsening-up sequence. So if you look at delta front deposits, we can see here an image that sort of is a repetition of what we were observing just a few seconds ago. So we tend to have quite a bit of mud that is interbedded with more sandy materials. So the mud is distinguished because it's usually darker in color, because it contains quite a bit more organic matter. So that could be an example of a flasher bedding, although in this case I don't see clearly the cross stratification, so it's difficult to judge from this figure. But yes, for sure we have an alternating set of muds and more sandy materials, which are these white horizons. So when you have combinations of siltstone, sandstone and shaly materials, many times you refer to these sequences as delta front deposits because they are not sand dominated or gravel dominated. So these are sections of a delta that are dominated by suspended load, basically, which can travel for significant distances off the coast and form plumes. And this can travel for several kilometers or tens of kilometers in some cases. The main contributing factor to the transportability of these plumes of suspended load in seawater is the carrying capacity of fresh water, which is usually less dense than seawater because it does have a lower salinity, and so it tends to float basically and stratify and form essentially a shallow layer in seawater that is essentially formed by fresh water with the abundance of sediment, and so you have a process that is helping with the dispersion of these plumes, which is water stratification. Here is an example of these major plumes. I think this is the Mississippi Delta, so that's in the States, and it's again the discharge of suspended load in the Gulf of Mexico, which can again transport the mud for tens of kilometers. So again, in this case we see how the delta is well protruded and how it's actually the sediment get dispersed also laterally, and it's influencing this bay with the accumulation of muds also along the coastline. And also all this other region is really influenced by the muds, so all around this digitation of the delta. So these are the levees, which will form in some cases swamps where the water and vegetation can grow. In fact, you can recognize very close to the main channels, so quite a bit of vegetation in this image. In this context, also the delta plume is favored by displacements that are related to local currents, so it's also important to mention that the seawater inherent currents can influence the capacity of the muds to travel significantly off the coastline. Grain size has also a big implication in controlling the form of a delta. So there are not only factors that are related to the condition of seawater, such as wind and wave action, we have that the sediment that is supplied will have an important role. So when you have conditions in which you have mixed loads that come of, for example, a meandering system, so we have relatively fine-grained material, we tend to get much more extensive depositions of muds in delta planes. So in these conditions, usually a fine-grained delta will form relatively small sandy mouths, and so the bar deposits will tend to be relatively concentrated. And then you have a much larger and dispersed fine-grained delta front that forms. So similarly to the example of the Mississippi case we saw before. So remember, the sand will be deposited in the delta channel and in the levees dominantly, and then we have that there is a sorting that occurs. So progressively moving away from the delta, we have what is called a sediment fallout, which is dominated again by suspended load that will derive from the river mouth and accumulate peripherally. Another process that is commonly associated with this delta is the effect of turbidity currents. So we discussed already the BOMA sequence, but we can have smaller events that are forming off a delta that will lead to major accumulation of muddy deposits at depth. And this is linked to an increase in density in sort of deposits that have earlier accumulated in the delta plane and sort of concentrated then on the delta front and get removed by these mass or granular flow events. So debris flows essentially can form off a delta front and they will cause a massive redeposition at higher depths away from the coast. In this example, we see a delta that is prograding into shallow water. So often the morphology or the depth of seawater in a coastal region is quite influential in controlling the distribution of sediment. So we can see here a meandering river that essentially form a couple of bar deposits which are fairly extensive. So again, the volume of sediments and the ability of prograding deltas will be determined in this case by the fact that we are in a shallow sea. In this case, the delta from facies will be all deposited in relatively shallow conditions, and often these conditions can be affected by wave action, which further contributes to the lateral extent of these sediment accumulations. So in many cases also we will get more sandy and gravelly deposits, especially if the sediment is derived from rivers that carry consistent bed load materials. However, the fact that this accumulation can spread out laterally will ensure that these accumulations are relatively well sorted. The contrary is true if we look at prograding deltas that have a slope that usually exceeds the 2 degrees, so we get very rapidly into relatively deep condition with respect to seawater surface. And so often this influences the dimension of the sediment accumulations in prograding delta. So we get more restricted accumulations of gravelly and sandy materials. So as you can see, we have a relatively small delta top, and we don't almost develop an extension really of fine-grained material, which would be localized in the delta front, which is absent. Instead, we tend to develop turbiditic current, so you have a canyoning and a much broader deposit forming at the base of the shelf. So coarser deposits will be essentially remobilized to form debris flows, and these will be represented by a mixture of relatively fine sediment and more coarser fractions. So we get unordered sequences that are again represented by thicker accumulation of turbiditic currents. In some cases, meandering rivers we saw can change their course. So this will result in avulsion, which is basically the development of multiple delta lobes in the context of this type of depositional system. So many times there are three factors that will be key to the avulsion of deltas. The first one is the change of the slope of an existing channel through delta prograding. So if you have that the sediment accumulates, you can modify the morphology of the channel. In some cases, the sediment we saw, like the example of the Mississippi River, will extend as a protrusion. So we form a delta protrusion. And this usually is causing a preference. So many times protrusion will extend the distance that the water needs to go through before it reaches the mouth of the delta. And so this is causing often an instability. So naturally a river system will prefer a shorter path to reach the ocean, which often leads to a change in the course of the river system and causes avulsion. And the last aspect is periodic flooding, which will break levees. So if you have marine transgressions, many times they can influence the course of the river system and so negatively affect a specific channel, and so it will cause this type of process in which we start with the development of a lobe, and then we have a sudden switch in direction and we form a secondary lobe, and then again we switch back. So we have multiple switches of the delta channel, which will sort of lead to a sequential overlap in this apron, which is represented by a succession of multiple delta fronts and delta tops. This is an example instead of a river-dominated delta. So we are comparing those deltas like the Mississippi River, which often are little affected by tides and waves. So if you have really quiescent condition and really shallow conditions, so you don't have big slopes, in those instances we have good opportunity to see a river prograding very rapidly towards the ocean and forming these distributary channels and levees that again link with these prodelta deposits through the mouth bars. So the channel form is mostly maintained, which is commonly related to the development of vegetation in the levees, which will stabilize them. So we tend to maintain the levees, and this ensures that we maintain also the channel deposition and the progression of the channel as well, with well-developed overbank areas. So in many instances, the levees will be dominated again by bed load or suspended load. In most cases, the suspended load composes the levees, and this of course depends if you change the channel conditions or not, but if you maintain a channel, in most cases it will be the bed load that accumulates on the levees. Instead, the coarser fractions will be accumulating at the bottom of the channel as well as in the major opening, so where we find the delta top accumulations. If instead we have prevalent winds, often if these are acting at an angle with respect to the coastline, we will develop parallel sets of islands or sandbars, which tend to cause a lateral extension of the sandy mouth bars, basically. So you get more elongated bodies, which are often called spits. So sand spits will develop on the sides of the delta, and often these will lead to the formation of internal lagoons, which we'll discuss later. So in this case, progradation is slower because of the action of the waves. So essentially the waves will rework the bedrock materials, and so you get again a change in the morphology, and as a consequence of that, a lot of the sediment that we find in sand beaches often is the result of this action of reworking of material that is derived from delta accumulations. An example here of a sandbar that illustrates well the dynamics of the waves that are essentially reworking some of the sand inside an embayment or a lagoon, and these are good examples of wave-dominated action. So the repeated movement of the waves tend to shuffle the sediment in more quiescent areas that are sort of more prone to sedimentation and deposition. In many instances, we characterize the coastline as erosional or depositional coastline, depending on this type of switches in energy. In some instances, we have that the tide currents will be rather more important than the wave action. And so we tend to have tidal currents that switch back and forth and tend to, again, reorganize some of the sandy and gravelly material that is accumulated at the mouth of a delta. So this is the example of the Ganges River in Bangladesh. So often we have these currents reworking and forming these tidal sandbars that are usually elongated in the parallel to the direction of the tidal flows. So in this case, overbank areas on the delta top become essentially partially tidal flats, so areas that are flattened by the action of the tidal flows and characterized by abundant muddy materials in many instances. So the delta top is often susceptible to flooding, which often is causing the development of brackish waters, which tend to accumulate quite a bit of organic materials as well. So these are highly vegetated domains, especially in tropical regions. So remember that the tidal currents will rework the sediments at the river mouth into elongated bars, which are commonly perpendicular to the shoreline. So these will be modified mouth bars, which usually can display, not always, but in some cases we'll have the herringbone stratification, so the bidirectional cross stratification, which is again related to the polarity of the tidal currents. We also find in these conditions also the characteristic mud drapes, which are those features related with flusser bedding. So cross-bedded strata are often present with sandy material mixed with muddy material that form these drapes on top of the cross stratification. One example of these shallow marine environments, in this case we think now at the switch. So if we move off a delta, what's going to happen? And many times we find, for example, classic coasts and estuaries instead of having deltas. So estuaries will be embayments which sometimes are linked also with a prograding delta, but it becomes usually a negligible or less prominent feature of the coastline. So we're going to review now some of these characteristic accumulations of sediment that are off the deltas in many instances. So in many cases, if we think of a free coastline away from a river system, we can distinguish a couple of coastlines very similar to what we saw for different type of delta depending on the depth of seawater and the velocity at which we can sort of reach the deeper part of the offshore or the shelf. So we often distinguish erosive coastlines from the depositional coastline. So usually depositional coastlines are relatively shallow, so they have a gentle gradient. You see the image here. You can recognize them because if they are gently sloping, many times you have extensive body of water that is relatively shallow, and so it's subject to extensive wave action. So a lot of the energy that is caused by the wave motion and development will be dissipated across a relatively large area. Instead, when we have a reflective coast, which is a coast that have usually a sharp cliff or relatively steep slopes, so you get really deep very rapidly, you tend to have little waves and they tend to be quite concentrated, and so they have a big erosive action on the coastlines, and this results in a range of morphologies really. So we have a variety of features that we can form. So we're going to review some of the features for, again, these dissipative coastlines versus reflective coastlines, which are much more erosive, and so they can sort of remove from the coast quite a bit of material because of the increased effect of wave action. So remember, these reflective coasts are usually represented by steep gradients, so energy will be much more pronounced and focused along the coast, and so for this reason you tend to have that both the bedrock and loose material can be removed from the coast and redistributed by the wave action. Okay, if we now review some of the examples, we have a gravelly beach here. So many times the action of the waves is repeated over time. It's very cyclical. Of course, in this case we have convergence of tidal movements with wave action, but in some of the dissipative coastlines the waves have sort of a leading action in the sorting of materials. In fact, if you look at these unconsolidated sediments, they are dominated by gravels. And in fact, in the shorelines, we tend to accumulate the coarser fractions. So in the foreshore environment, we have mostly gravelly and sandy materials that will accumulate along the coast. So this depositional coastline then will transition towards the offshore environment. Transitional offshore environments will be more characterized by finer fractions, very similar to what we saw for the transition from the delta top into then the delta front environment with all those plumes and accumulation of suspended load material, which is much finer grained. So in a way, the action of the waves is actioning in a similar fashion. So it's selecting materials, so we get good sorted and mature sediments on the coastline in correspondence of the foreshore and also partly of the backshore environments. So in this example, you see some of the cobbles that we find on the gravelly beaches. These have clearly a granitic composition and have been extensively reworked. So the foreshore is a good environment where you will find quite a bit of rounding of the class, and you can find really coarser fractions. Over time, if you get enough lithification going, you will get massive accumulations of conglomerate, which will get cemented usually with muddy material or quartz-rich materials as well. And this is an example of a conglomerate which has been deposited and consolidated. So you have a gravelly beach that is now has become essentially a rock. In this other example, we see instead a condition of relatively high energy that is focused on a coastline that is more an erosive coastline. So you can see the steep cliffs. In this case, they look as calcareous cliffs or siltstone sort of dominated cliffs, because I can recognize some of the stratification here. So that's a bedded sequence of likely sedimentary rocks. And often the seawater will exploit some of the stratification and form terraces which tend to favor the ponding of water, which again, it's salty water. So hydration and deposition of salts will contribute to the weathering processes, so oxidation. So you can see some of the reddish oxidation of some of these sedimentary rocks that have been acting upon this cliff and will progressively cause the fragmentation and wedging processes that we already reviewed in earlier lectures. So you see accumulation of blocks that then get transported away when storms develop along the coastline. In terms of morphological features on a beach, again, we can recognize the foreshore, which characteristic stratifications that form. So many times on the foreshore you will accumulate several strata of sand or gravelly material, which can be then preserved if you lithify the sandstones. Often this is an area that is continuously perturbed by wave action, and it's separated by a berm that instead is a ridge that forms in response to the energy of the major storms that occur. So many times the wave action can increase if you have flooding events related to these stormites. So storms will accumulate quite a bit of sediment in exceptional circumstances, forming a berm which protects the backshore environment. So often, if we can recognize crustal stratification and deformation of a berm, we can identify the depositional environment that is typical of the foreshore and backshore conditions. Off the backshore, usually you have a coastal plain, which will include many times the action of aeolic winds, so you form beach dunes and ridges just on the back, which again it's material that commonly get transported by wind off the beach and is accumulated in a more sort of low energy environment found in the coastal plain. An example of a beautiful tropical island with a characteristic beach. Not much we can say here, just the desire, I would say, to spend some time on these whitish sands. So many times the sand color will be a function of the material that accumulates on the foreshore, and since we are in a shelf setting, especially in tropical regions, we have quite a bit of biota that develops in the neritic zone, and so most of the shelly material that forms from these organisms is fragmented and accumulated on the foreshore environment and leads to this whitish sands. This color will change if, for example, you have a granitic coastline, or if you are off the coast of the Hawaiian Islands, you get those black volcanic beaches. So again, the type of sediment that you find on an island will be a function of the type of source materials that is available for this reworking. This is a real case example of a berm, so you can see the cuspated aspect of the berm and also the erosional surface that result. So you have essentially sloping sets of sands that were accumulated in the foreshore environment, which again is separated by the berm, which is the culmination of this cross stratification, and you have an erosional surface that separates the backshore deposits, which are more flat line in this case, or display a flat line stratification. Some example of the dune ridges. So remember that on the coastal plain we can accumulate quite a bit of material in response really to the movement of wind or reworking of wind of these loose materials that are found in the foreshore, and often these become stable forms because of the accumulation of vegetation that will grow on the dunes, and it will tend with the roots to provide a stabilization for the unconsolidated material. So you can see here a lot of shrubs developed on these relatively large dunes. Sometimes they can exceed the 10 meters in elevation quite easily. Many times this action of reworking sands and moving them across the coastline will cause the formation of estuarios and also lagoons. So we have an example here of a lagoon, which is a coastal body of water that usually is loosely connected to the open ocean, and this is because it's protected essentially by this effect of longshore drifting. So wave fronts will tend to rework the material and form these crests or beach barriers that are represented dominantly by these sandy materials. Sometimes if we have stormite, so storm events, will form a washover deposit which can invade the lagoon, which causes a change really in the stratification. So many of the accumulation we find in the lagoon can be influenced by seawater dominated processes, especially if we have sediment is moving across the inlet, but dominantly lagoonal settings are relatively quiescent. So we closer to the coastal plain we tend to form quite a bit of muddy and silty materials that accumulates in these domains. And so this will be commonly leading to the formation of mudflats, which are characterized by those forms that we mentioned when we were talking about the structures that form in domains that are relatively shallow and can be affected also by freshwater systems. So if you have a nearby river, for instance, you could have supply also of sediment coming from a heterogeneous source. So in terms of structure, we will find vegetation, so root structures, so a lot of bioturbation can occur, and also the formation of those polygonal cracks is common in this environment. So the condition required for the formation of barriers, most of the cases they will have to have significant supply of sandy and gravelly materials, and this is because of the internal attrition. They tend to sort of form more easily ridges, and these can then protect from the ingress of seawater. The other aspect is that commonly we need to have a significant motion of waves. So waves driven longshore drift of sediment is a requirement really to move the sediment off the mouth of the river system and essentially redeposit it along the coast. Many times also we need to have situations in which the tidal range is relatively small, so microtidal conditions are the best when you have tides that are on the order of few centimeters, really not really the meter level, because the beach barriers usually are just a few meters in terms of elevation. Some examples here of these beach barriers, and of course you get multiple crest lines, and they can be curved as well as a function again of the change in wave action over time. And so in this case we have a prograding set of beach barriers, which are a function of the fact that progressively we are accumulating sediment in different portions of the coastline, but probably moving away from really the source, which will be here. So you can think this as a part of a delta in which we are extending along the coastline with the accumulation of sands, and you can see also some of the washovers that result from some of these storms that commonly form periodically or seasonally. If we have a coastline that is influenced by both the wave action and tidal processes, so let's say we have a region that is more on the mid-tidal or macro-tidal regions, so very extensive reflux of currents, you can see usually larger inlets with the increase of the tide effect, and these commonly are represented by a dualism in the depositional system. So you form flowed tidal deposits in the lagoon, but also ebb tidal deposits will be more on the seaside, and so this often leads to more complex depositional systems. Because of the flooding, we usually have a more extensive flooded area, which is the subtidal region that forms in the coastal plain, so that dark green area. So usually you develop much more extensive mud flats in these more tidal dominated lagoons, and so this of course will result in all those more vegetated region, more brackish water, so many accumulation of peat can occur in these embayments. So barrier sediments will be washed through the channels and often will be deposited as a flowed tidal delta. So again, remember that these tidal dominated environments will be represented by these polar currents. So bipolarism is common, and so you will have those flowed tidal deposits which look like deltaic deposits, so they can form cross stratification that is quite unique and is represented again by the accumulation of dunes and ripples which can migrate in both directions, so towards the lagoon as well as towards the sea. Some example of the extensive shorelines in tidally dominated coasts. So you have very extensive mud flats. So the strong tides will prevent the formation of a barrier system along the coast, basically. So tidal mud flats are the form that dominates, and they are often flooded with the water. So this is an environment that is particularly good for the formation of brackish water, preservation of organic matter, and accumulation of vegetation as well as soil formation. Another important depositional system is more of a mixed depositional system. So these are estuarios where we have meandering rivers that actually contribute as well to the sediment load that is accumulated in a central lagoon. And so these are commonly leading to the formation of a bayhead delta, and these are usually more reduced deltas. And they are commonly called estuaries, which will be essentially the marine influence portion of the drawn valley, because many times this will form on pre-existing valleys. So you have an erosional phase in which usually the seawater is at low level, so we can have secular variations in which we are inside a valley with a river system, and then we have a marine transgression over time that will take the lead and essentially flood a pre-existing V-shaped valley. So this commonly results in an estuario, and so you tend to have a situation where you still provide sediment with the river system, but you have that most of the valley has been flooded. So you form a drawn valley. So these transgressions, of course, will lead to the formation of other things. So many times you form the central lagoon because you have the similar type of process we saw before, in which you are creating beach barriers again. So we get a depositional system that is much more complex, because on the distal parts closer to the barrier reef, the beach barrier, we will get mostly coarser sediments accumulating off the beach barrier. When you have washovers, instead inland closer to the mud flats, we tend to have accumulation of fluvial related sediments. So cross stratification, prograding deltas will form, which is again represented by those inverse grading with the formation of a delta top, which is represented by coarser fractions, and then prograding sediments with cross stratification that is represented by more silty and muddy materials. So coarsening-up progradational successions forms with the channel and overbank facies building out over sands deposited at the channel mouth, basically. In the central lagoon, instead, we will find the fine-grained deposition, so those silts and shales, which are often rich in organic materials, and then we have often the beach barrier, which is more represented by sand and gravel, that is again reworked by the wave action. One example of these, a major sandbar at the mouth of a wave-dominated estuary. So you can see the inlet here, which is sort of this valve that actions and connects sea with the lagoon. Depositional settings in tidally dominated estuaries are more similar to what we saw for those deltas in the Ganges River. So we tend to have again a flooded valley. So the difference here is that we have a coastline that is has been previously eroded by the river system, and so we have essentially a major valley that developed, and after we have that a marine transgression is leading to the flooding of that valley, and this essentially form an inward pattern and leads to the formation of tidal flows that form tidal bars of coarser materials. So in this example we lose those barriers formed by sandy and gravelly islands that were redistributed along the coastline. So in this case it's more the tidal currents that are forming these accumulation of coarser fractions, which are therefore parallel to the tidal flow directions. And on the side, when we meet the coastal plains, we tend to form tidal mudflats. So mudflats will develop on the side and result in similar type of structures, sedimentary structures as mentioned earlier. So this environment is characterized similarly to delta that are dominated by tidal currents, by herringbone cross stratification, cross-bedded sandstones, and also those flusser beds and lenticular beds, which are characterized by mud draping. So these deposits, often, especially the ones that are formed on the central part, so along the tidal flows, will be usually heterolithic, so they will consist of alternating layers of sand and mud with again an orientation that is perpendicular to the flow. Some examples again of these sandbars in a tidally dominated estuary. So you can see the erosive effects of the current. So this originally was a sand spit that has been eroded away and remolded into more elongated sandbars that are, or midbars that are oriented consistently with the prevalent direction of the current. This is an example of the tidal mudflats you will form in areas that are adjacent to the coastal plain and often are influenced by tidal creeks. So we have laterally forming tidal creeks which can get flooded, so you have accumulation on the sides here, on the banks of quite a bit of mud, which is contradistinct in this case by the abundance of polygonal cracks. And with this final image we have completed lecture 14. So to sum it up, we have seen most of the transitional environments from freshwater to saltwater systems with an emphasis of deltas and coastal related environments. So we have seen dissipative and erosive coastlines with relative sedimentation patterns, and also discussed some of the lagoonal settings. In the next lecture we will move to other marine environments, so more related with the distal shelf, and so we are going to mention some of the biota and some of the environments that are more typical of rift systems, and then we'll discuss also the deep abyssal plains and the type of sedimentation that is found in those regions. So this lecture is concluded, and we will continue again with other sedimentary environments and complete the sort of a series of lecture on sedimentary environments with lecture 15. And we reached the end of this lecture. So in the next lecture we're going to talk about the shallow marine environments that are more dominated by carbonates, and also the evaporitic environments, and then we will move to the deeper abyssal plains and discuss also some of the sedimentation that is found more distally. Okay, so that's to conclude this lecture, and yes, complete also this discussion about sedimentary environments.